We started to talk about basically conditional probability. We did lots of examples on that one, and we talked a little bit about what are independent events, right? And now we keep continuing by doing one example. On multiplicative rules, and the example is this. Each rule of the 5 dice together is 1 try. Each try is independent of the other tries. In other words, the results of try 1 has no influence on try 2. So, what is the probability of not getting a single winning roll in 5 tries? And a winning rule has 3 of a kind and 2 of a kind, but not 5 of a kind. In other words, we have like 3, 4 and 2, 6. It cannot be all 4s or all 6. So this is how we define the winning. Okay, think about it. So what we want to do is we want to calculate the probability of lose, 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 and lose. Which we know that because they are independent, it is the probability of lose multiplied by probability of lose for 5 times, which is equal to probability of losing power 5, right? Now, how many ways can we lose? Michael, how many ways can we lose? Many ways we can lose. But there is only one way that we can win, in general. So, we have many ways of losing, so sitting down and writing it, one possibility is that we see how many ways we can lose and write them down. Or, we know that probability of winning, the situation is very rare, so I can write that probability of lose is complement of probability of win. So it's 1 minus probability of win power 5, right? Think about it today when you go home till the next lecture. Think about it, how we can calculate the probability of win. How we can calculate the probability of win. And
the win could be...
The win will be 3 of one kind, 2 of another kind. So this is one condition. We have only one condition for winning. But we understand that it can be 3 of 1, so 3 of 2s, 3 of 3s, and if this is 3 of the 1s, in the other 2 they cannot be 1. They can be 2 of 2s, or 2 of 3s, or 2 of 6. They cannot be 2 of 1s. So think about it and see how we can calculate it. And if, in order for you to see that you are correct, this should be 0.386. And remind me next week when we have the class, I will calculate it for you. Okay? I give you one more exercise to think. I think this week, either today or tomorrow, I will post the first homework also. And the example is this. The exercise is this. Bag contains 10 red stones and 90 blue stones. What is the probability of selecting red, blue, red in that order when sampling? In other words, we want to calculate the probability of red, blue, red. Now, you tell me, assume the first one that I picked is red. Does it affect on the second one to be red or blue? No. The first is red, the second one is blue. Does it affect on the third one to be red? No. We want it to be red to be, because we want to calculate it, but we don't know. I mean, the first one can be red, the second one can be blue, the third one can be blue. So they are not affecting on each other. In other words, it will be the probability of red, probability of blue, and probability of red. But we have to be careful about something. This is the probability of first one red. This is the probability of second red. So you have to keep this one in your mind.
So it's solid.
Sorry?
No, it's solid.
Yeah, but it's exercise. I mean, it's not a homework.
But it's only on condition if you put the rock back inside the stone.
Yes, we do not put back. I think last week we said that in all the examples we don't put anything back. If you take it, we take it. And if we need to put it back, I will tell you that we take red and we put it back. So, okay, I can solve it now. I mean, here, what is the probability of having red? 10 over 100. This one is 9 over 98. And this one, 99. Actually, you can notice that I could say, this is the probability of red, first, probability of red, second, probability of blue. For this one I have 10 over 100, 9 over 99, 90 over 98. We will get the same results. Although we understand that the probabilities are changing, but the result of the multiplication is the same in this specific example. Now, let's do one more example, but not a numerical example, something of the conditional probability in which we are using also the Venn diagram. So we can come to a result which you can use that formula. And it is, let A, B, and C be three events. A, B, and C. Then the probability of A intersected by B given C is the probability of, what is it?
Intersection B, intersection C.
It's A intersected by B intersected by C divided by probability of C, which means that this is that intersection part, right? Probability of A given that B intersected by C is happening is probability of A intersected by B intersected by C divided by probability of B intersected by C. Probability of A union by B given C is probability of A union by B intersected by C divided by probability of C. What is this expression? A union B B intersected by C. Can you expand it?
A intersection C.
Yes.
Union A intersection.
So, the probability of A union B intersected by C is the probability of A intersected by C union B intersected by C. And we remember, what is the probability of A union B? It's probability of A plus probability of B minus probability of the intersections, right? So this is equal to the probability of the first term plus the probability of the second term minus the probability of the intersection. Right? So I want to put it down into here. From here I get that probability of A union B intersected by C is equal to, what I had in here was probability of A intersected by C plus probability of B intersected by C plus probability of A intersected by B intersected by C divided by probability of C. I have one denominator, so I can put it in for each of the terms. So probability of A union B given C.
A minus.
Yes, it is a minus. I wanted to check if you're slipping or not. Now, you tell me, I go. What is probability of A union A intersection C divided by C? I mean probability of C.
I don't know how to say it in English.
Say it in any language that you like. P
P,
A given, it's called given C. Okay? What's your name? Eva.
Yeah.
Eva. Okay? Eva will tell us what is this?
Is probability B intersected by C.
B given by C. And what was your name? Joseph? Raymond. So what's this one?
Probability of
Maybe you want to cheat from here?
A intersected by B given C.
A intersected by B given C. Okay, friends, look, probability of A union B was the probability of A plus probability of B minus probability of A intersected by B, right? Probability of A union B given C is probability of A given C plus probability of B given C minus probability of A intersected by B given C. Now, when we are talking about the conditional probability, we will talk about bias rule. Now, we will talk about random variables later, and then we will come back to the bias rule again. Many of you have taken the pattern recognition from me last semester. We had the bias rule in order to make decisions. And I will remind you a few of the terms that we had last semester in here so you can see that how they are related. But imagine that we have S and we have A and if this one is X, this part that I have shaded is X. Thomas, what is this? If this part is X, what is this part?
Starts with C.
Sorry?
It starts with C. Complement.
Yes, it is complement. It's X prime because they're complement. Now, if we look at X and X prime, can you tell me that what they are called with respect to S?
S. X union X.
Yes, X union X prime is S, but what is their intersection? Empty because they are complement of each other. But X and X prime with respect to S, what do they do? We said that if one set union another set is S, and that set union the other set is also empty, intersection is empty, then we say that these sets are doing something to S. They are
Partition.
partitions. If the intersection is empty, we call them mutually exclusive. So independency, no, we cannot say anything about the independency here, right? Now, let's look at something else. This blue shading part and this red shading part. What are these? What are these?
Partitions of A. Partition.
They are. So what can you tell me that what is the formula for them? I mean, I cannot write partition of A, it should be something. Like here, I didn't say partition of S, I said X, it's called X. What about this one?
A
No.
intersect X.
A intersected by X. So this one is A by X prime. Right? Then total probability was stating that the probability of A is the probability of X union intersection A plus probability of X prime intersected by A, which is the probability of A given X multiplied by probability of X plus probability of A given X prime multiplied by probability of X prime. And we had this formula yesterday. So, this is when we have only two partitions, a very simple situation. Imagine this is A, partitions of S. So imagine that BI's, we have K partitions of S. So here we had only 2, and now imagine that we have K partitions. So the total probability generalization, the total probability generalization states that the probability of A is, now probability of A is the probability of A intersected by each partition plus the probability of A intersected by another partition plus so on. So it is saying that this is I from 1 to K probability of A intersected by BI. And we understand that there might be a partition, I don't know, B, let's say 6, which then it doesn't have any intersection with A, which means the probability will be 0 in there. But we can add 0 and nothing will change, right? And this, by using the conditional probability, is I from 1 to K probability of A given BI multiplied by probability of BI. Right? Like what we had in the case of 2 partitions. For partition, keep this one in here for a minute, and let's say for partition R, we have probability of BR given A. In other words, I have this partition, we want to see the probability of BR given A. So what's the definition, what's the formula for this? It's intersection of BR by A, so the R's partition, divided by probability of A. Right? Which is probability of A given BR multiplied by probability of BR. Is it correct? Look, probability of BR given A is probability of BR intersected by A divided by probability of A. Right? Probability of A given BR is probability of A intersected by BR divided by probability of BR. Right? And these two are the same. So from these two I understand that probability of BR given A multiplied by probability of A is equal to probability of A given BR multiplied by probability of BR. Right? Now, we had this one before. So, now what I have here is probability of BR intersected by A. We know that probability of BR intersected by A is either probability of BR given A multiplied by this, or it is probability of A BR multiplied by probability of BR. So I have written it in here. Right? Divided by probability of A. Let's call it equation 1. Let's call it equation 2. From equation 1, And equation 2, if I write here, you can see, right? Probability of BR given A is equal to probability of A given BR multiplied by probability of BR. What is probability of A? This is probability of A, right? So I put it here. Probability of A given BI multiplied by probability of BI. Probability of BI is known as prior probability. Probability of A given BI is called likelihood. So if this value is high, it means that A is very similar to BI, so the likelihood value is higher. And the probability of BR given A is called posteriori. Posterior. And this is a formula that we use it in pattern recognition in general if you want to use probability in order to calculate whether we belong to a class or not. And this is called the bias rule. Well, let's do an example to see how we can use this formula. In a manufacturing plant, 3 machines known as B1, B2, and B3 make 30%, 45%, and 25% respectively of the products. So we have 3 machines which are producing the products, and each of them is producing different percentage of the products. It is known that 2%, 3%, and 2% of the products made by each machine respectively are defective. If I produce something with machine 1, 2% of that one is faulty. With machine 2, 3% is faulty. With machine 3, 2% again is faulty. Now, suppose that a product is found defective, a product found problematic, what is the probability that it was made by machine B3? Imagine A is the event of being defective, and the question tells what is the probability of being B3 given that it is defective. Now let's write down the facts that we know about this question. We know that we have 3 machines. And the probability are 0.3, 0.45, 0.25. And we know that the probability of defective, given that this is B1, is 0.02. Probability of it is defective, given that this is B2, is 0.03. And the probability of defective, given that this is from machine 3, is 0.02. So these are given, and I am being asked to calculate